Hello, I'm Marty Triola, and I'm here to talk to you today about statistical graphics. Histograms are so important that they've been given their own section, and in this section, in this segment, we're going to be talking about frequency polygons, ogives, dot plots, stem plots, bar graphs, Pareto charts, pie charts, scatter plots, and time series graphs. Just in general, we might think about all of these in terms of an overview. Do we really have to learn every one of these graphs and learn how to do them manually? No. The main objective here is to really try to determine how best to graphically illustrate the data in a way that conveys the true nature of the data. What's really important about the data? How do we get that across by using a graph? And we should really always try to think about plotting some kind of a graph to give us that insight. It would be real easy to miss out on some important characteristics of data if we just skipped over a graph and just jumped into some type of analysis. So I'm going to start out with a relative frequency polygon. In the book, we're going to talk about frequency polygons and relative frequency polygons. And an excellent application of frequency polygons would be to compare two different data sets. Here on the same graph, I have pulse rates of men and pulse rates of women. The little legend up here indicates that women are indicated by the solid line. So here are pulse rates of women, and men, the dotted line. Here you have pulse rates of men. And by putting them on the same graph with the same scale, I could look at this and I could see that, well, the pulse rates of men seem to be somewhat shifted farther to the left. And this suggests to me that pulse rates of men tend to be a bit lower than the pulse rates of women. That just jumps out of the graph, just jumps out at me. And so this would be a topic that I would be really interested in pursuing using some other methods of statistics that we'll learn about later on in the course, methods for comparing two data sets analytically apart from just a subjective interpretation of the graph. But those relative frequency dot plots, or relative frequency polygons rather, are excellent tools for comparing data sets. Dot plot, that's a handy graph for showing something about the distribution of the data, and yet, in a sense, you're keeping the original values. You're not rounding them off. Like here above 60, I see 3 different values. Now, these are pulse rates of females. So this particular dot plot shows me that there are 3 females among the group that were studied, 3 of them that had pulse rates of 60. All of these numbers aren't filled in. The graph would get too busy. But this is 64 right here. So 4 females at pulse rates of 64 and so forth. So by looking at the general shape of the distribution, I see something that's very roughly bell-shaped. That's an important observation, a bell-shaped distribution. It's one that we're going to call a normal distribution later on. But also, when I look at this graph very carefully, something else really jumps out that's quite significant, quite important. I see pulse rates of 60, 64, 68, 72, 76, 80, 88, 98, I think this is. They're all multiples of 4. All of these pulse rates happen to be multiples of 4. And I think about that. Now, in reality, is there anything about women that would inherently and naturally make their pulse rates multiples of 4? And the answer would be no. They should not be multiples of 4 typically. So I would think, well, how did this happen? How did this happen that I ended up with pulse rates that are multiples of 4? Well, thinking about it and talking to people in the healthcare fields, a common way to measure pulse rate is to count the number of heartbeats in 15 seconds and then multiply it by 4 to get the number of beats per minute. And that's why these particular pulse rates in this data set happen to be multiples of 4. So just by looking at the dot plot, I got to learn something about how the data were collected. That's pretty neat. Oh, I did want to do this just to illustrate how quick and how easy it would be to construct something like a dot plot. I'm going to go over to the computer and I'm going to fire up Minitab. Okay, I'm clicking on Minitab. It's loading. It just takes a second to load. Now I'm going to have to navigate a little bit to get the right worksheet. Let's see. In my particular computer system, it's kind of buried in here, but I can get to it. For you, this will typically be going to a CD, perhaps. Here I have the CD, and if it's on your CD, this is what you would get. Appendix B datasets, applets, extra datasets, software in the TI-8384 app. But I'm going to click on Appendix B datasets because I'm in Minitab. I'll select Minitab, and I want pulse rates of women, and that's the female health data set. So I'll click on that to open it. And it's column 5. So I'm going to go up to a graph, scroll down to dot plot, and you can see all the graphs that Minitab has built in. Scatter plot, histogram, dot plot, stem and leaf, bar chart, pie chart, time series graph, a lot of the graphs that we talk about in this section. Here I want a dot plot, so I'll click on that. I want a simple dot plot, and I want pulse rates of women. Click OK, and there it is. See that? Very quick, very easy. Just a few clicks of a button, and you've got it. Stem plot, and here again I'm using the same data sets, the 40 pulse rates of females that are found in Appendix B in the back of your book. And a stem plot is set up so that each data value is broken up into a stem and leaves. Here's a pulse rate of 60, another pulse rate of 60, and the third pulse rate of 60, then a 64, and so forth. Here's a pulse rate of 96, pulse rate of 104. There were no pulse rates in the 110s, like 111, 112, 113, none of them. But there was a 124. And in this format, I could see that this 124 seems to be out here all by itself. It's a potential outlier. Okay, we're calling an outlier a value that's very far away from the vast majority of all of the other data. Potential outlier here. And if I think about that, a 124 pulse rate for a woman, that's pretty high. That would be a pulse rate I'd expect to see from somebody that's been doing some exercising. So I'd really wonder about that. How did that occur? In this particular case, I can't go back and identify the person by the way the data were collected. But potential outlier. So a stem plot lets me keep the integrity of the original data. I could go back and I could recreate the original 40 values here, and I could see something about the nature of the distribution by looking at the shape here. And also, there are several cases where we want the data sorted, arranged in order, and that accomplishes the sorting as well. These data are in order. Okay, so there's some nice advantages of a stem plot. Now we're going to look at a scatter plot. A scatter plot is an excellent device for illustrating an association between two variables. Okay, we have paired data. In this example, I have movies. I've got a number of different movies, and I've got their budgets paired with their grosses in millions. For example, this movie out here, it had a budget of something like roughly $225 million, and it took in a little bit over $300 million.